4.6 elastic potential energy in simple harmonic motion. I apologize for the audio. For some reason the microphone is picking up this wild hum. I went to my car where it's quiet and still somehow the microphone's picking up a wild hum. Feel free to pause the video as we're going just so you can record things into your notes. Now, so far we've looked at gravitational potential energy and kinetic energy as two forms of energy, and now we're introducing spring energy. In order to do that, we first need to look at the Hooke's law and what an ideal spring is. It's governed by this equation, F equals negative K delta X, right here. So what is this equation saying? Well, it's saying that the force that a spring exerts is equal to the distance that you compress it or stretch it times a spring constant. That's what this is right here, that negative K. Now it's negative because if you compress a spring, the force the spring applies is in the other direction. If you stretch a spring, then it pulls against you. So that's what the negative is doing. We have these nice pictures up here that I've reproduced just here, just so you see how I draw it. But the idea is when there is no stretch or compression, when the spring is at neutral, then there's no force. And for an ideal spring, whether you stretch or compress it, it does not matter. You still get the same force out. And you might notice that for this spring, there's no limitations on how far you can stretch or compress it. So even though there might be some physical limit on a spring when you're compressing it, the ideal spring equation just assumes infinite stretch or infinite compression. Now the spring constant is just that, it's a constant. So you can think of it like a slope. And its units are newtons per meter. There's a mini investigation we'll do, a little lab, but we'll do that on another day when I'm in class. So we have an example here. A spring hangs, must be like an autocomplete, and has weight put on it which deflects at 7.9 centimeters, and the mass is 0.46 kilograms. Determine the spring constant. You can always refer back to your textbook if you need to. Well, if we draw a free body diagram, we have the spring holding the mass in place and gravity pulling down on it. And it's hanging at rest. It's not moving. So that means F net equals 0. And the sum of the forces will be the force of the spring minus the force of gravity. So we get Fg equals Fx, mass times gravity equals Kx. Now you're going to say, I thought the formula was negative Kx. Well, we just take the magnitude of the equation. We don't worry about the negative sign because the negative sign was implying direction. And when we set up our equation here, we're accounting for direction. So we just take the magnitude of the formula, just Kx. Now we can rearrange for K. K equals mg over x, and we can sub in our values. So we get 0.75 times 9.8 all over 0.079. I think that's the deflection. There you go. Don't forget to convert to meters. Alright, I haven't done the calculations ahead of time. I think we need it for the next step in here. You can see all the games that my kids play on this tablet. Where's my calculator at? Okay, so we had 0.75 times 9.8 divided by 0.079. So 93. 93 newtons per meter. Determine the displacement if a Oh, I used the wrong mass. I used the mass from the second section, classic. So where's the backspace? I think it was 4.6. So 57. What would the displacement be if it's 0.75 instead? So now that we have the spring constant, we can use that to determine a different value. So we can start from right here in our setup, mg equals kx, but now we're solving for the displacement, the stretch, if we used a different mass. So we get 0.75 times 9.8 divided by 57. .13. Now C says, calculate the net force if the same mass is compressed 5.3 centimeters past rest, then let go. So now, since it's not hanging at rest, what we're doing is we're holding the mass in place with some compression. So from the point of view of the mass, the free body diagram, not only is the force of gravity pulling down, but we have the force of the spring pushing down as well. And so we have F net equals ma now. It's an accelerating mass. So we're going to have ma equals Fg plus Fx. Acceleration is equal to mass times gravity plus kx all over m. So we get 0. I'm assuming we're going to use the same mass as the second example. Alright, forget the compression. Alright, for the sake of time, I'll let you figure that out. And finally, the last part is asking for it was asking for net force and then acceleration. So first it's asking for net force, so you can just do the sum of these two together, and then for acceleration you do the part that we just did here. Alright, so we've talked about spring force, but our goal is to talk about spring potential energy. So we turn the page, we have this graph here that as we increase the stretch, we have a linear increase. The slope is k. We have a linear increase in the force. And so if we want to figure out energy, then what energy is equal to force times distance. So what we're doing is we're figuring out the area under the curve. And that shape is very easy to calculate because it is a triangle. So work equals force times distance. The force is equal to kx. That's the, or another way to look at it, sorry, is saying the formula for a triangle is 1/2 base times height. The base is delta x, and the height is the force up this axis, and force is equal to kx. So we put that together, then you get 1/2 k delta x squared. So that's where the derivation of the formula comes from, right there. teenager compresses a pogo spring, what's the energy stored? So yes, it's as easy as you think. It's going to be 1/2 K delta X squared. Oh no, it's not as easy as we think. We don't have K. But we have the mass and we have how far it is compressed. So we're going to start by solving for K, just like we did before. F net equals 0. We have a mass here that's compressing a spring. The spring's pushing up to keep it in place. So we have 0 equals Fx minus Fg. That's equal to Kx minus Mg. So K is equal to Mg over X. 18 times 9.8 divided by 0.18. 18 times 9.8 divided by, I already forget, 0.18. Newtons per meter. Oh, what am I doing? A 42 kilogram. Boy, I'm in rough shape here. 42 times 9.8 divided by 0.18. 2286. 2286 newtons per meter. Now we want to figure out the energy stored in the spring. So that's 1/2 K, 2286, 0.18 squared. So 37 joules. Okay, I think I'm going to stop it there. I'll take the time to derive this formula for the period of oscillation for simple harmonic motion another time. You have lots of work cut out for you. There's the practice questions there relating to energy, and there's the practice questions there relating to force.